Okay, questions to start. I have one thing that we need to talk about a little bit, but any questions? So today was going to be sort of catch-all for SN1, SN2, E1, E2, B1. E2 we will start after the exam. Galen?
So your rankings for those major products, when you have like the same amount of calculators, what if one is like a better calculator? Does that matter? Or is it
No.
just not?
No. So for instance, if you had this molecule and we said we're going to do an E1 mechanism, which basically means that I'm going to do this reaction without a nucleophile present. So maybe I put this alkyl halide in something like, I don't know, a solvent like DMSO or an aprotic solvent that will not act as a nucleophile, and I heat it. Then here's my alpha carbon, here's my beta carbon, here's my other beta carbon, and there's my third beta carbon. So if you're just writing the products of this reaction, we're going to lose HCl, and we're going to draw a double bond to each of the beta carbons. So that means that, for instance, I would have this double bond, the double bond to, let's say, beta carbon A, beta carbon B, and beta carbon C. So this would be, for instance, product A. And then the double bond outside the ring to the CH2 would be product B. And then having the double bond down would be having product C. So if I have those three products, A and C are the same, and B is a different product, and this actually isn't the molecule I wanted to draw. Let me change it. So in this case of A, B, and C, which one would be the major product? A and C are the same. So what would be the major product, A or B? Julia? A? Do we all agree that A is going to be the major product? Because A has 3 alkyl groups attached to it, and B has just 2. If we change the structure of this and I put a CH2, CH3 group on here instead of a CH3, and I do the same E1 reaction, I would get the same, basically the same 3 products, only now what's going to happen is I'm going to have a methyl group attached to the double bond outside the ring. And then I'd have a double bond down. So I would still have products A, B, and C. Products A and C are still the same. But of A and B, which one is the major product? Maybe we should vote on that. Does everybody agree that A and C are the same? So it's just going to be A, B, or C would mean that they're both the major product. So of these two, which one is the major product? A, B, or both of them would be C. Okay. Does everybody have an answer? So A, B, or C, which one is the major product? Okay, I've got 18 C's. I've got 4 A's and 2 B's. So counting up the number of carbon groups that are attached to carbon A, there are 1, 2, 3 carbon groups attached. For carbon B, there is this H should really come up there. And so we've got 1, 2, 3 as well, so they're tied. So this is the issue that does it matter what the 3 alkyl groups are? No. A methyl is the same as an ethyl, is the same as a propyl, is the same as a ring. And that also held true for carbocations. 3 methyls, a tertiary carbocation with 3 methyls is no different than a tertiary carbocation with 3 ethyls. The only time the carbocation would be more stabilized would be if it has a double bond next to it, which are the allylic and the benzylic systems. So that would make the carbocation more stable. Okay. And actually, whether the double bond is inside the ring or outside the ring, I've said to people we're not going to quibble about which one is more stable. I actually have software on one of my office computers, and I ran the calculations last night just because I was curious as to which one of these two were more stable. And it turns out that they only differ by 4 kilojoules, which is basically 1 kilocalorie. And so that's not enough energy to favor one over the other. So you would actually get a mixture. And it turned out the double bond outside the ring was more stable than inside the ring. But the energy difference isn't very much. So we would definitely get a mixture of those 2 products if we were to do that reaction. So I think we're justified in just counting number of groups and not worrying about whether the double bond is inside or outside the ring. Okay. So it doesn't matter what we're just counting alkyl groups, doesn't matter what they are. And this molecule for those three products, that was the practice problem, right? Okay. What other questions? So we'll talk about rearrangements here after the exam. I could get into rearrangements today, but I think it would take up the entire time. Julia?
So will B1 be on the exam? Like what else is going to be on the exam?
I added on to, there's a question on Piazza. There's an entire list, and I added some things on. So if I remember correctly, EZ, RS, determining whether same enantiomers, diastereomers, meso, same not meso, with pairs of molecules. I would know definitions like what's a definition of an enantiomer or a meso or a diastereomer. You'll have to write the mechanism and write the products of SN1 reactions. Same thing for SN2s, and the same thing for E1s. So if you look at some of the older exams, you'll see I ask mechanisms, and then I also ask to write the products of the reaction. And we'll link SN1 and E1 together here in a minute. So we have to modify the chart that was made to tell which reaction goes with which mechanism.
For EC and RMS, are you going to name something?
No, you just have to tell me whether it's EZ or RS, I guess. If you look at some of the older exams, you might see that for some of the cyclohexanes, I've given you kind of a name and asked you to draw the structure, or I've given you the structure and asked for the name, the cyclohexane name. But I think in this case, what I'm probably going to do is just You just have to do R and S. So RSEZ, same meso. Those make great multiple choice questions because they'd be multiple choice questions anyway. So we might do part of the exam with the Scantron and then the other part with mechanisms. That will help me get it graded faster. So that would be like last year's exam. Okay. Right. So in chapter 9 they talked about alcohols. And I want to go through the dehydration reactions of alcohols. What's today? Today is Wednesday. On Monday, we did, in the afternoon class, somebody asked about alcohols to begin with, so I did alcohols. We did alkyl halides, so I've got to flip-flop them today. But alcohols undergo what are called dehydration reactions. So a dehydration reaction just simply means this. If you have an alcohol, you have that OH group is eventually going to become my leaving group. And I say eventually because I need to do something to it to begin with. It's still going to be the alpha carbon, and then I'm still going to have beta carbons. But in this case, what I'm going to do is I'm going to lose water in this reaction. That's the net result. So in this case, I can form the double bond to the carbon on the end, or I could lose this H2O and I could form the double bond in the middle. Okay. So the net result is I'm losing water. That is called dehydration, because I'm dehydrating the molecule. I'm losing water. Okay. But this will not occur on its own. And the reason why this reaction just won't occur on its own is because OH, when it leaves, would have to leave as an OH minus. And OH minus is a strong base. And what do we know about strong bases? They make poor leaving groups. They make poor leaving groups. So I just can't do this reaction without adding something. Well, okay, let's go ahead and add H+. And what's H+ going to do? You're going to hear me say over and over again for the rest of this semester, for the rest of the year, if you have me, I'm going to say over and over again, whenever you have an oxygen molecule and you add acid to it, the first step is always protonate the oxygen. That's always going to be the first step. So we're going to protonate the oxygen by having the OH bond the H+. And this is the reverse step of our SN1 reactions, where the water would come in, or where the water would lose H+, the oxonium ion would lose H+ to give me the final product. So this is the opposite step. So now what I've done by protonating the oxygen is I have turned OH, which won't leave, into water, which is a much weaker base, and therefore a much better leaving group. So simply by protonating the OH, I can now make it leave. And so now I'm going to break the carbon-oxygen bond. I'm going to form water. And then I'm going to have my secondary carbocation. The carbocation basically then becomes the alpha carbon. I look at all the possible beta hydrogens that I can lose. In this case, I have 2. And so I'm going to take this bond. For instance, for this one, I'm going to lose this H+. So I'm going to lose an H+, and I'm going to form the double bond there. So let's say this is hydrogen A. I'm going to lose the beta hydrogen A+. Or I can lose the hydrogen, let's call it B, HB, and so then I'm going to lose HB+, and I'm going to form the double bond at the end. Does that make sense? So then which is the major product, A or B? Or both? A? Are we all in agreement it's A? Okay. So then A would be the major product. This mechanism this is going to be classified as an E1 mechanism. And what I need to do is broaden my terms out. So we found that not all SN1 reactions were 2 steps. They could have been 3. Here's an E1 reaction that is 3 steps because I need to protonate the OH first. The mechanism that hopefully you drew for the practice problems was just 2 steps because we were using a halogen. Okay. So an E1 or any 1 mechanism, anything that's labeled as 1 goes through a carbocation. And anything that's labeled 2 does not. That's our definition. So 1 reactions go through a carbocation intermediate, 2 mechanisms, there's no carbocation intermediate. So that helps us broaden our definition of 1 and 2 out a little bit more. So this would be classified as an E1 mechanism. Since it's an E1 mechanisms always give you, as the major product, the most stable alkene. And so that's why A is the major product. Now, was everybody able to write the transition states for losing the H+? So the transition state, let me write the transition state for forming A. So I'm going to lose HA to give me my final product, and my final product would have then an H+ with it. So the transition state then, we're going to have partial bonds on any bond we're breaking and partial bonds on any bonds we're making. So that means we have a partial bond to this hydrogen and the partial double bond. Then we're going to average the charges. To be honest, we don't even have to think about averaging the charges. What we have to think about is every atom that has a plus charge in the reactant or product, that's where the delta plus is going to go. So this carbon has a plus, so it's going to have a delta plus. And what else needs the delta plus? The hydrogen, because the hydrogen is lost as a H+. So this would be the transition state then for that reaction. So the only thing I'm adding here is we write a partial bond on the bonds we're forming. So this is dehydration. And actually, Zaitsev, when Zaitsev proposed the idea that when you do a reaction, an elimination reaction, and you get the major product being the most substituted, he didn't use alkyl halides, he used alcohols. That's what Zaitsev actually used. So his conclusion was, whenever I do a dehydration reaction, I always end up with the most substituted product, if there's a choice of products, meaning there's more than one beta hydrogen. Okay, so that's how we do dehydration. There's just this little issue of, so where did the H plus come from? Because I actually have multiple choices on the H plus, and if I do that, it's going to change the product potentially. So let's say that somebody wanted to do this reaction, and they said, well, I'm going to choose as my H plus, I'm going to use HBr, or HCl, or HI, any HX. That's my H plus I'm going to use. So what would happen? What would happen is we would protonate the oxygen. And this is critical. I'm going to protonate the oxygen, and then if this is a secondary or a tertiary system, I'm going to lose the water. So I'm going to lose the H2O to then form my carbocation. Okay, there's a temptation sometimes, for particularly in this case, to have a nucleophile come in and kick the water off. That occurs in a primary system, but not in secondary and tertiary. Although it'd be interesting to do the kinetics on that just to verify that fact. But in this, what we're going to do is we're going to say, once you protonate the oxygen and you make the water molecule, if that water molecule can leave and leave a stable carbocation, it will do that. And so that's what it does. But now the problem is that my counter or my conjugate base of HBr is Br minus. So what's the Br minus going to do? It's going to come in and add to the carbocation, so that now what I did was I basically substituted the OH for the Br. So this would become a substitution reaction. Since it went through a carbocation intermediate, it is now SN1. So we would classify this as an SN1 mechanism. It's a 3-step mechanism, but it is SN1. So that's one. This is a way to substitute a halogen for the OH group. I just use HBr, HCl, HI, HX. It's not dehydration, though. Okay. So the H plus, the source of H plus makes a difference. All right. Is everybody with me so far? So the only thing different about this reaction is I had to protonate the OH to get it to leave. If I just tried to react OH, an alcohol with Br minus, I would get no reaction. And you probably will see some of those in the practice problems, particularly I'll have two reactions. One will have HBr and one will have Br minus. And the one that has HBr goes faster because the one with Br minus is a no reaction. You can't kick off an OH group. It's too strong a base, it will not leave. So then if I want to do dehydration, what do I have to do? I got to choose an H plus that doesn't have a conjugate base that's a nucleophile, basically. So what I can do is I can say, well, let me take my alcohol, but now let me use H2SO4 as my source of H plus. What's the advantage of H2SO4? Once the H2SO4 donates the H plus to the alcohol, protonates it, I end up with an HSO4 minus as my conjugate base. And we already know that basically for HSO4, that if it's a strong acid, its conjugate base is going to be weak. And in general, the weak bases are going to be weak nucleophiles. But in this case, if I wrote the structure of this out, it would look like this. That would be the structure of HSO4 minus. And the reason that that's a weak base is because it's very stable. Why is it stable? Because it has multiple long periods of silence by me mean it is not a rhetorical question, meaning I'm not going to answer it right away. If it's a rhetorical question, I usually jump right on the answer. So why is HSO4 minus stable? Because it can form multiple resonance structures. It can form multiple resonance structures. I think we talked about this because the book had introduced the idea of using this as a leaving group. And it was a great leaving group because it was a terrible base. So it's going to be a lousy nucleophile because it is a very weak base. It's a very weak nucleophile because it's very stable. You could make the argument that it's kind of sterically hindered too as a nucleophile. And we'll get to the steric hindrance of nucleophiles next week. We also need, with either of these reactions, we also need a little heat to go with this reaction. And heat is sometimes abbreviated with a triangle. So when you see a triangle in organic, it means heat. Okay. So if I use sulfuric acid is going to do dehydration. And we already wrote the mechanism for the formation of those products a few minutes ago. So the reactions of alcohols then could be SN1 or they could be E1. It's really going to depend on the source of the H+. You want to do SN1, use HBr, HCl, use an H plus with a nucleophile. You want to do dehydration, use H2SO4. You can also use H3PO4, phosphoric acid, same philosophy. H3PO4, its conjugate base is really stable and a weak nucleophile. And then you can combine these two together with, like what we're going to do in lab next week. If you take, we're going to take butanol and we're going to react it with H2SO4 and sodium bromide. And we're going to do that reaction. So what's going to happen is the H2SO4 is going to protonate the OH, and then I've got Br minus to come in and do an SN2 reaction and kick the water molecule off. And so when you look at that, when you look at the pre-lab lecture, go through the mechanism of that. So we're going to use a combination of the two. And the book, I think, has a couple problems where they've done that as well. They've had sulfuric acid plus sodium bromide, and the final product should be the alkyl halide. It should be the substitution reaction. Okay, so that's where alcohols fit into this. Because typically we dehydrate alcohols. We have pretty good success in dehydrating them. The problem is, if we wanted to form the double bond that's least stable, I don't have a mechanism to do that right now. We will at the end of next week, but we don't have that right now. So those were the two big E1 reactions in the chapter, with alkyl halides and with alcohols. Questions? About any E1? Okay, last thing that I would like to make sure we're all on the same page with is predicting reactions. So I looked at this one and I said, oh, well, that's an SN2 reaction. How was I able to predict the reaction mechanism? And there's a couple of things we should know. We should know that primaries only undergo 2 reactions. And I'm going to broaden this out and say 2 reactions, meaning that there's no carbocation intermediate. There can't be, because primary carbocations don't exist in here. Tertiaries only undergo 1 mechanisms. They only undergo 1 mechanisms because they don't undergo 2s. And they form stable carbocations. That leaves secondaries in between. What do you do with a secondary? Well, to evaluate a secondary halide, we need to know one other fact. And that is that when we have a weak nucleophile, like water or alcohol, the only thing that they can react with, they must react with a carbocation. Those are not strong enough to kick off a halogen. They're not strong enough to undergo SN2. So weak nucleophiles must react with a carbocation, which means that they must undergo 1 reactions. Okay. So with those 3 facts, primaries only undergo 2s, tertiaries only undergo 1s, and weak nucleophiles have to react with a carbocation, we could set up a reaction table and say, what happens when you react an alkyl halide with a strong nucleophile? What happens when you react it with a weak nucleophile? Primary, secondary, and tertiary. Our example of a strong nucleophile is anything with a negative charge, weak nucleophile, alcohol, or water. Okay. So I would say memorize this table, but you don't really have to memorize it, because hopefully it makes sense. So Primary alkyl halide plus strong nucleophile. What mechanism are we going to get? SN 1 or 2? Hold up fingers. Make sure the 1 is this one and 2. 1 or 2. Okay, it's going to be an SN2. Why? Fact number 1. Primaries only undergo 2 reactions. Okay. What about primary and a weak nucleophile? What are we going to get? We're going to get no reaction. Why? Fact number 3. Weak nucleophiles only react with carbocations. Can primaries form carbocations? No. So therefore, we're going to get no reaction. We can skip down to the tertiaries and say a tertiary halide plus a strong nucleophile is going to give me SN1. Because tertiaries only undergo carbocation mechanisms, so SN1. How about the tertiary plus the weak nucleophile? Also SN1. That's the double whammy, right? Tertiaries can only undergo SN1 and weak nucleophiles can only undergo SN1. So it leaves the secondaries in between. And so what we're going to do is we're going to kind of make rules here for the secondaries based on those 3 facts. Now, we may modify those reactions later on, but when we first start learning SN1, SN2, E1, and E2, it's better to deal with sort of 95% or 90% of the reactions, and then we'll talk about the 10% that may be anomalies later on. I remember when I first started teaching, I taught at Kansas State in the middle of the dead center of the country. Right? That Manhattan, Kansas is right in the middle. And it's very isolated, although it's more cosmopolitan now, I guess, than it was when I was there. The guy who was teaching the real organic, because I just taught the organic for pre-vet students and dietitians and other things, and same class, basically. But he's like, I don't think I believe anything we teach them about SN1 or SN2. And I'm like, that's not good. So I said maybe it's because you're focusing more on the exceptions to the rules than the rules. I don't know if you like that or not. I haven't seen them since. But if we focus on the exceptions, we're just going to be confused. And you might already say, I'm confused already. Well, you would be more confused. So we're just going to stick to the big pictures. So primaries, 2s, tertiaries, 1s. So if I have a strong nucleophile with a secondary halide, I'm going to say that goes SN2. And I'm going to say secondary plus a weak nucleophile. The weak nucleophile can only react with the carbocation. Can a secondary form a carbocation? Yes. So that will allow me to do SN1. So with secondaries, it's not going to be the secondary. It's going to be, what is it reacting with? Strong, SN2, weak, SN1. Now, you may have noticed that I wrote my SN1s over to the left. Well, SN1, the first step in the mechanism is the formation of the carbocation. We now have a second mechanism that involves the formation of the carbocation. So whenever we get SN1, we're going to get some E1 products. So we should modify our table here and say, whenever you get SN1, you're going to get E1 as well. So typically what we'll do with problems then is if I give you a reaction, I'll ask you what's the mechanism, and then I'll ask you to write the major products of the reaction. Now that's separate from a mechanistic question. I'll ask you to write mechanisms as well, but then I'll also give you some reactions and say, what's the mechanism? What's the final products, possible products? What's the major product? So when it's SN1 and E1, you're going to get the SN1 product, but then you're also going to write all the possible E1 products, and you're going to circle the major product. Or products, as we saw from today's practice problem, if there's more than one. So SN1 always goes with E1, or there'll always be a little bit of E1 product with the SN1 reaction. We really can't do E1 all that effectively unless we use alcohols and H2SO4. This chart, unfortunately, is for alkyl halides. It would roughly be the same if it was alcohols, but we're just going to strictly use alkyl halides here. So this is the chart that's going to guide you in terms of what is my mechanism.
Did you say that if it was a strong nucleophile, it wouldn't undergo E1?
If it is a strong nucleophile, it would not undergo E1, except the problem is down here that once you have a tertiary and you form that carbocation, the alkene product you make is probably going to be highly substituted. So you're going to get a little bit of E1 product. I'm not determining which one is the major product here. I'm just saying you're going to get some E1. And in theory, if you try and do E1 with anything but an alcohol, you're going to get a little SN1 as well. So that's the chart that we're going to use for this. That's also the chart that can be helpful in determining which reaction goes faster or slower. Okay. And I guess I didn't put that on the possible list for Monday's exam as well. If I gave you two reactions, which ones go faster or slower? But I might include that when we get to Friday, and we can go over a couple of those problems if necessary. Okay. All right. So, questions? All right, then do you have a particular problem that you would like to do? Okay, let's say I gave you this reaction, and my question is, number one, mechanism. Number two, write the possible products. Number three, what are the major products? Okay, Julia. Oh, sorry. I'm sorry. For this kind of problem, if I gave you this, I would actually ask you. There's two ways I can ask this problem. I probably mix them together. My first one would be write the complete mechanism for this reaction. But in that case, I'm going to tell you whether to do it SN1 or SN2. I'm sorry. I'm going to tell you whether to do it SN1 or E1 in this case. So I'm going to say, like over here, I'm going to say write the mechanism for E1 for the major E1 product. Or I'm going to say write the mechanism for the SN1 product. So I'm going to limit you in terms of the mechanism that you're going to write for that. And I do mean all transition states as well. The second problem would be just write the products of the reaction and tell me what mechanism it would be. So don't write the mechanism, but just write the final products. So that's the one I was going to do here.
For SN1, would the like being substituted onto the alpha ring be OH? Or like what would be the?
Well, that's a good question. So let's do this. So let's do this in 3 minutes, simulating the time you'll have on the exam. Well, hopefully you'll have 4 instead of 3. And we just wasted 30 seconds. Mechanism. What's the mechanism of this reaction? SN1 and E1. Okay? So for what's the SN1 product going to look like? What am I going to replace the chlorine with? An OH group. And what are how many possible E1 products do I have? Alpha carbon, beta carbon, beta carbon. Do each of the beta carbons have a hydrogen they can lose? Because if the beta carbon doesn't have a beta hydrogen, you're not going to form a double bond there. So in this case, the answer is yes. Both of them have hydrogens. So that means I could simply write the products like that. Right. So there are my 3 major products. And what I would further do is I would say write the SN1 product. If the reaction is SN1 and E1, write the SN1 product, write all the possible E1 products, and then circle the major one. So in this case, of products, of alkene products A and B, which one would be the major product? A or B? So 1 is A, 2 is B. Okay? On 3. 1, 2, 3. 1, I see. That would be the major E1 product. So that's the one I would circle or write as major. Okay. So for mechanisms, I'm going to ask you to write the mechanism of just one of those. Kaylin?
I'm confused because in that part it just said that like the secondary room is only SN.
In my chart, I added the E1 to it. Okay. Julia?
Would you have to choose between the SN1 product and the major E1 product? Like, is the SN1 product always going to be a major product?
Yes. So it'll always be, if you're doing SN1 and E1, it will always be SN1 and then all the possible E1s. Because there is only one SN1 product. There can't be more than one unless you're doing rearrangements, which we're not.
About major products, like SN1 will always be included in.
Yes. Yes, as long as it's SN1 and E1, it will always be part of that. Okay. Okay, so